I'll first talk about what I'm just euphemistically calling pipes. This is how we connect things together to make something a networked application. And then we'll talk about many different kinds of networked applications. We'll start with the simplest kind, which is client-server. There'll be 3 examples of that: secure shell, network file system, and the World Wide Web, which is the 3 fairly important applications. And then in the next class, in the class after that, we'll talk about other things like BitTorrent and YouTube and Facebook and Twitter and things like that, DNS. So these are applications you probably use every day. But what we'll do is we'll go one level deeper. We'll see how these are actually put together. And we'll get some hints. If you were to go out and make your own networked application, how would you do it? So to start off this, it's important to understand a little bit about how an application becomes a networked application, right? So a standalone application, let's say you're playing a video game on your screen, or you have a spreadsheet. It's standalone. In other words, you're just interacting with the local application, and the application isn't really talking to anything else. Compare that to a browser. The browser actually is nothing more than showing you what it's fetching from the web. So those applications would stop working when the network is down. Okay, those are network applications, sort of by definition. So how does it work? To understand this, I'm going to kind of give you an analogy, and actually this analogy sounds kind of stupid, but it's actually it works better than you think. So this is something my kids made over the winter break. So this is an old-fashioned, well, actually, this is fine. Old-fashioned communications technology is called tin cans and string. Okay, how many of you actually tried this out? So you could raise your hand. Okay, so those of you who hasn't played with tin cans and string? Okay, so for those of you who don't know this very high-tech method of communication, what it is you take a tin can. Something that works very well is those juice things where you have concentrated frozen orange juice or something like that. Well, first you drink the orange juice, if it's empty. After that, you make a little hole at the back, and you attach a string to it, and then you attach on the other side to it, and if you stretch the string taut, and you can actually speak over here, and the other person puts it to their ear. There. It's a happy person with a big ear. They can hear it. And the thing is, it can go around corners. You can have tin cans and string, go quite long distances. As long as it's taut, it actually works. So what can we learn about network communications from the fact that it's the tin can and string? Well, the first thing is obviously it's a networked application. Okay, it's a voice application. You can think of it as Skype. Okay. Sort of. If you have somebody who lives in the apartment complex, you don't need to do Skype. You can do tin cans and string. But there's more to it. One of the things is that it's unidirectional, right? So one person is speaking, okay? Oops, nose. Yeah, you need a nose. Okay. So one person is speaking, and the other person is hearing. So it's unidirectional. All right. So a unidirectional channel like this is called a simplex channel. And simplex means it's one way. Okay, that's the term that we use. It's a term so here's an example of another simplex channel. It's radio broadcast, right? You turn on your TV or radio, and the TV tower is going to send out information, but you can't send it back, right? You can only hear what they're broadcasting. You can't, shout back. You can shout back at your TV, but they won't hear you. Okay, that's a simplex channel. Actually, it's not simplex. It's actually something more complicated, because you could interchange it. This person could hear and the other person could speak, and then the direction changes. So it's it goes either one way or the other. So it's not actually simplex. What it is what's called half duplex. And half duplex means that at any given moment in time, it can be communicating in one direction, but not both at the same time. An example of this actually is walkie-talkie, right? If you ever use one of those walkie-talkie things, if one person speaks, the other person cannot. So you got to take turns speaking, and that's what's called half duplex. But we can have a highly sophisticated arrangement of 2 tin cans and strings, so like so. And now what we do is we put one tin can to the mouth and the other to the ear, and we label them appropriately. And then what happens is that if your mouth is here, and your ear is here, and on the other side, this is your ear and that's your mouth, then what you get is, if you view this together, this becomes something that you can speak and talk at the same time, which is kind of useful, and we call that a duplex channel. Okay? So this is the kind of the essentials of communication, is that a channel is intuitively clear as being a communication path between two different communicating endpoints. That communication channel has three modes: simplex, half duplex, and duplex. Simplex, it goes only one way. Half duplex means it can go one way at a time, but you can switch. And duplex means you can go both ways at the same time. All right? So that's one lesson you get kind of from this tin cans and string altogether. Let us suppose that there are two businesses which communicate frequently with each other. Okay? For example, it could be a business, full of lawyers in this one building. So let's see, which is a company that is always being sued? So it's Apple, right? So let's say here's Apple, corporate headquarters. So let's see. That's Apple. And right next to it is Apple's lawyers. Here's lawyers. And a bunch of people at Apple are calling up the lawyers all the time, right? So they want to talk to each other, and the way they do it is that they basically have lots of tin cans and strings going all the way from front to the other. Okay? So each person has actually pairs, because they probably want to talk and listen at the same time. So we have these dual pairs of things, and there's lots and lots of them. Okay? And it would stretch across, I don't know, a couple of kilometers, something like that. And the problem with this situation is there's lots of wires going around, right? There's lots and lots of wires going around. And it's kind of wasteful. So suppose there are 1,000 lawyers here and 1,000 employees here. If anybody wants to talk to any lawyer, you need 1 million pairs of wires. Okay? You need 1 million pairs of wires, because you need 1,000 people here. And you need 1,000, actually you need 2 million, because you have two pairs, right? Two pairs of tin cans. So you need 2 million wires to connect the Apple with the lawyers. Even Apple, which is the richest company in the world, is not going to be too happy with 2 million wires going to just one other building. Okay? And of course, Apple actually has like 15,000 people, and they probably have 15,000 lawyers as well. So it's a lot more than that. It's 225 million communications. It doesn't really work. But so somebody clever at Apple, and I believe there are some clever people at Apple, might suggest the following idea. They say, look, let's do this like this. We're going to not need so many wires at all. What we'll do is we'll have this special person here and a special person here. And these two people are going to actually have all the wires coming in locally, like so, 1,000 wires from each side, or 2,000 wires from each side. And between the two of them, this is going to be one wire. And this is the way it's going to work. When this person, let's say Apple A1 wants to talk to lawyer L1, A1 tells this person over here, hey, I want to talk to L1, all right? So this person calls on that one wire to this other peer person over here and says, hey, I have a message for L1. So whatever I tell you, tell it to L1. And this other person picks up the wire to L1. And so that's the way it goes. So A1 will talk to, let's call this R1 and R2 for somebody who routes messages, because you're setting up a route. So A1 talks to R1 and says, I have a message for L1. L1 shouts to the tin can, this is a message for L1. And so A1 says, sue Google, message for L1. R1 says to L1, sue Google, and they go and sue Google, okay, or something like that. What we've done is, by introducing these two nodes, intermediate nodes R1 and R2, we've cut down on the number of wires that you need. Secondly, what we've done is that we've introduced the need to have a name called L1. Okay. So because earlier when A1 just picked up this tin can, it was, it was the name of the person at the other end. So all you needed to do was just speak into that wire. There's no need for anything beyond that. However, at this point, what's happened is that R1 needs to know whom to give it to, right? So we actually have a bit of a problem because there may be two sets of lawyers. So there's lawyer 1, and there's another set of lawyers 2. And so now R1 has to decide, should I give it to this bunch of lawyers or that bunch of lawyers? And then within those bunch of lawyers, which lawyer gets it, right? So we need what you think of as an address. Just like you have an address for your post, in your postal address, you say, give it to this person who's on this street, who's on this city, etc. In the same way, you want to say, give it to this lawyer, and this one says, oh yeah, that lawyer that goes on this connection here, so I'm going to give it here, and then I'm going to send it off to this lawyer here, right? So immediately we see that by reducing the number of wires, we need to introduce a few things. First, we need addresses. And second, we also need to choose between these different lawyers, right? Because when it goes here, this guy has to figure out, is it a lawyer 1 or is it lawyer 1000, right? Which one is it, right? And so we need, so these, we call these, in technical terms, we call them port numbers. And so we need to introduce addresses and port numbers, okay? Because we need to tell this router here which address to go to, okay? Which address to go to this address or that address, and within that address, which port number to go to, okay? So, and then I'm going to give you two last terms, and then I'll stop for a moment for questions. So the last two terms is, I've done something interesting over here. What I've done is I've shared this link between these two. It's this particular link actually doesn't belong to anybody, right? It belongs to everybody over here. They're all sharing it. And that sharing is called multiplexing. Okay, that's the sharing that's going on over here. And over here, what's happening is getting unshared. You're getting coming in together, and you're kind of splitting up all over. And this over here is what is called demultiplexing. Okay, so let me just quickly review what I did the last 10 minutes. First, we talked about this notion that a tin can and string allows us to have communication, which we call simplex, or actually more precisely half duplex communication. And second, I said that if you're going to have these two entities talking to each other, and there are lots of communication talking to each other, communication endpoints, lawyers and corporate executives talking to each other, we have too many wires, right? So what we're going to do is we're going to shrink it down by having all these guys come to one central point over here, and this talking to central point and then getting it out over here. We call that sharing multiplexing. Okay, it's multiplexing going on over here. And to require multiplexing, we need to, at the end, at this point over here, got to figure out where it goes, right? To figure out where it goes, we use port numbers. And to figure out whether to use this one or that one, we use addresses. Okay, so the address plus the port number uniquely identifies which destination it's going to when it's starting out over here. Okay, and finally, what's going on is that this router over here needs to have some way of knowing that if I have to go to this over here, I have to go in this direction. If I want this address, I want to go in that direction. So it has a way to route to a particular destination based on the destination address. Okay. When you had these direct wires from here to here, you could always call anytime you wanted. Okay, you could just pick up your tin can, and the other person was available. At least you're not going to be blocked by the network. As long as you're not out to lunch or something like that, you could get to them. You would not be blocked by the network. In this case, what's going on is that if this particular shared line is busy, this lawyer might be talking to that, sorry, this A1 may be talking to L1, A2 wants to talk to L5. It goes to R1, R1 says, hey, sorry, I'm busy. I can't make a call, right? So you get what's called network blocking, right? And in any situation where we have multiplexing like this, we're going to have blocking, right? So we're two or three ways of avoiding it. One way to avoid it is to make this link quite broad, right? What do you mean by quite broad? Well, instead of having one wire over here, I could have, let's say, 50 wires, because even though there are 1,000 people, chances are unlikely that more than 50 are going to be using it at the same time, right? Unlikely. Not that it's guaranteed, but it's unlikely. Perhaps on some special occasion, more than 50 would be going at the same time, in which case you would have blocking, but it would be a rare event. Okay, so that's one way of doing things. And the same thing actually shows up when we try to figure out how big a road should be, right? So we have ring road going around the campus, right? How wide should that road be? Okay. Well, we're going to expect a certain amount of traffic, and based on that we say, yeah, you know, about 10 meters, maybe 12 meters, or rules of thumb, whatever. But then there's convocation, and you know, the thousands of people showing up who weren't there before. So on that rare occasion, you're going to get backed up, right? So anytime you have any multiplex resource, like a road, like a bank teller, or you know, if you pick up your cell phone and it says network is busy, you know, you get this fast beep, 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 beep. You can't make a call because it's busy. All of those are because of a multiplex resource, and this is an automatic problem whenever we have any multiplex resource. Okay, so the second thing you could do is to put a buffer over here, and you draw buffers like this, like a stack of plates on its side. And what the buffer is saying is that I have a request coming in, but you know, just wait in queue. It's like a bank. You go to a bank, you can't get served right away. You're going to stand in the queue, and eventually your turn will come. Right? And if you size it properly, if things aren't too congested, eventually you will get out. Right? Same thing, you have a parking lot, you want to exit the parking lot, but it's busy, you just got out after a hockey game, so you know, the roads are busy. You're going to wait your turn, eventually you'll come in and you'll get out. Right? So you'll get service eventually, and that's the queue over here. Okay. So those are the two ways. And the third thing you could do is you could just drop the call. You could just send a message back to it saying, you know, sorry, you know, you can't go through. Or you can say, make a reservation, you know, call me, if you call me at 2 a.m., I'll be free, call me at 2 a.m. and that'll be okay. So you can make a reservation in advance. And so we'll come to these kinds of things in more detail later, but the problem shows up right away. Okay, so I want to talk about one more thing before we actually get into, you know, how to translate this into internet. And I want to talk about the following, again, the thought experiment over here. So let's go back to this same thing, and now I need my high-tech connection stuff here. Okay, so we'll use this. All right, so let's go back to a connection between app A1 and L1. So this is, I'm going to draw it using this thing over here, okay? All right, so take this connection between A1 and L1 over here. I'm showing this as this broad orange path, and what I'm saying over here is the following. This represents a communication path where if A is talking to L, it owns that whole path. Nobody else is allowed to talk during that time. So if this person is speaking, everyone is listening. If A1 is not speaking, just sitting there, you know, kind of thinking, doesn't matter. Nobody else can use this link over here. All right? This requires the following thing to happen. In the beginning, A1 is going to tell R1, I need a path. I need a path to go from here to there, and I want to own it. Okay, it's going to be my path. R1 says, okay, gives it, goes to R2 and says, A1 wants a path to L2, you know, nail it down, nobody else is going to get it, etc. all the way, and then this path gets set up, and until the path gets torn down, A1 to L1 path is established. Okay? So it's the first way of doing things, okay? Just remember that, the orange way. There's another way of doing things. The other way of doing things is like this. A1 sends a short bit of information, this green bit of information, with the orange bit in front. And the orange bit in front says L1, okay? And that goes to R1. R1 looks at the stuff in the header, as we call it, in orange, and says, oh, that's going to L1, and just puts it over here, the green bit of thing with the orange stuff in front, which says L1, and gives it to R2, and the R2 gives it over here, same thing, over here, it's L1. But it could be that immediately after that was sent, another bit of information may come from A10, for example, like so, which is going to L5. Okay? And, you know, so now this link at any given moment in time has one message, but you could have different messages going to different destinations at different points in time, right? From the perspective of A1, it doesn't really care. Whenever it needs to send a message in the green approach, it just sends it, and as far as it's concerned, the fact that this link is shared or not shared doesn't really matter. It's just whatever it is, right? However, from the perspective of network efficiency, it's a lot more efficient, because it turns out that most of the time, A1 and L1 are just thinking. They have short bursts of communication, and then the rest of the time, it's not busy, it's wasted, right? However, with this approach, it's not wasted. You're able to use it. So that improves the efficiency of usage of this link. Okay? The first approach is what's used by the phone network, right? So when you pick up your telephone or your cell phone and you make a call, what's happening is that you actually have a path, a virtual path, from your phone to the destination's phone, and that is, quote unquote, nailed down all the way from end to end. Okay? You pretty much own that path. You're paying for it, of course, right? But you own that path. That's like the orange system over here. And we have a special name for it. We call that connection-oriented system, because that's a connection. It's a connection-oriented. And so what we have is a system where you can sort of think of this intermediate path as really giving you an entire end-to-end, tin can and string. Okay? From your perspective, that's what you have. In the other approach, you have something called connectionless. What you need in connectionless is you need these headers over here. With these headers, you can figure out where it's supposed to go. And these are the two different ways of doing things. Yes, Tommy?
Is connection-oriented another name for a circuit switch?
Yeah. Connection-oriented. A circuit switch is one way of getting connection-oriented. Virtual circuit switch is another thing, but they're both connection-oriented. Yeah, circuit switch and virtual circuit switch. So we're not going into that right now. The concept I want to get across here is that with connection-oriented, the two endpoints sort of own that path. Nobody else is allowed to use it. Whereas with connectionless, nobody owns the path. You're sending these little bits of information which have a name as well, and these are called datagrams. Just like a telegram, it's a datagram. And the datagram header has the information of where it's going. Okay. So again, let me summarize what I said in the last few minutes. The first thing is that we kind of established that we want to multiplex this link, but there are two ways of multiplexing it. Okay, they're both multiplexing. In one way, when at a particular point in time, that multiplex link is actually dedicated to a pair of communicating endpoints, right? And nobody else is allowed to use it, even if they aren't using it. And that's what we call connection-oriented. In the second approach, the link is never dedicated to anybody. Okay, what happens is that you have these little datagrams, and the router looks at the destination address on the datagram header and sends it, and then it demultiplexes it, and off it goes into the destination, and life is good. So the first approach is one that's used by the telephone network, and the second approach, datagram approach, is what's used on the internet. And the reason why the internet is allowed to do that, it can do it, is because we need over here a fast processor. We need something that can look at these packets, these datagrams, look at the header and decide where they go, and do it very fast. Okay, how fast? Okay, can you guess how fast routers do it today? Okay, so today's routers can do this kind of processing, looking up in 5 nanoseconds. Okay, so what's 5 nanoseconds? So we know what speed of light is. Okay, actually, most people don't know the speed of light. What is the speed of light? Does anybody know what the speed of light is? Yeah?
3 times 10 to the 8?
What? That's right, 3 × 10 ⁸ meters per second, or 3 × 10 to the 5 kilometers per second. 1 second, it goes 3 × 10 to the 5. Okay, how much does light go in 1 nanosecond? Okay, 30 centimeters, about this much. Okay, so light has traveled this much, and it's already forwarded a packet. Okay, that's how fast today's routers go. Okay, so every 5 nanoseconds, I mean, imagine that. light has traveled 150 centimeters, it's about this much, 150 centimeters, almost exactly this much. That's all that light has traveled, and you've already figured out what the header is and where it's going, okay? So this is truly astonishing, that they're going this fast. And yeah, you can go buy one of these things, and you can build internet components today with these speeds. Okay, so this is possible today. This is what people are doing today. So it kind of works. It works pretty well. Okay, so I've thrown a bunch of jargon at you, and I want to just quickly go over that, and we'll take a break. So we've talked about this notion of multiplexing, addresses, port numbers, demultiplexing, connection-oriented, connectionless, datagrams, and headers. Okay, and if I hope all of those kind of concepts are clear. And they all follow essentially from this thought experiment of tin cans and strings. There's nothing really super complicated about them, okay, just common sense. And as you'll see, almost everything in networking is common sense. Very little is not common sense. Okay, just have to think about it. It's pretty straightforward. Okay, good. So moving along. Okay, that was a bit longer. Okay, so I'm going to now continue with this notion of pipes, and I'm going to kind of switch from tin cans and string to how we implement tin cans and string on the internet. Okay, so I mentioned already that the basic idea in any communication, whether it's tin cans and string or the internet or anything, is this notion of having these two endpoints, okay? The two endpoints talk to each other, right? Over some path. That path may be just one connection, right, which is this direct connection, or it may have some intermediate elements, which we call routers. But from the perspective of the application, it doesn't matter. From the perspective of the application, all we're doing is we're going to tell the network, okay, which is in this case the router, I want my information, my datagram, to go to that destination, okay? And once you do that through some magic, okay, which we'll study in quite a bit of detail in the next few weeks, but for now it's just magic. Through some magic, it'll appear over there, and then this guy sends a reply back, and so on. So what we have is this notion of this, what we call an interface. And we have some communicating endpoint that wants to send data and receive data, and this other interface, and the other communication endpoint is going to receive and send data. And in between is what we often call the network cloud. Okay, it's this, we don't really care what it is, it's something magic, right? What is it interface? The interface basically says send, and when you send it, you want to say to this address, to this port number, and this piece of data. Okay, and that's the interface that the internet provides. It's pretty straightforward. And on this side, you basically say receive, and you can't say where you're receiving from. You just say receive on some port number. Okay, and when you sit there receiving, eventually somebody's going to connect to you, and then you get the data. Okay, so we call this kind of communication client-server communication. So this is client, and this is server, and we'll have more to say about that in a moment. But in a nutshell, this is how we write networking code. It's pretty straightforward. The server sets up, it calls a receive method, procedure, whatever you want to call it, and that tells, and that goes to the networking interface, and the network is saying, okay, there's somebody who is listening on some port number, which is that. It's like this over here. So this lawyer is saying, okay, I'm listening on port number L1, okay? So anybody wants to listen to L1, wants to communicate to L1, send it to me, all right? That's what that server is going over here. This client is like the Apple official over here who's saying, I want to talk to L1. So it sends the network, I want to talk to L1. So I want to go to law firm 1, lawyer L1, and this is the message I want to send. And the network in between, which is these guys down here, arrange things so that that data is delivered to the lawyer. Okay, that's it. Strictly speaking, there is no conceptual difference between the two. A port and an address are both, as far as we are concerned, a way to identify a particular endpoint. What this recognizes is that inside one building, for us, inside one computer, there could be more than one endpoint listening, all right? And instead of assigning them their own address, which is for various reasons wasteful, it's easier to assign them port numbers, okay? So you kind of think of having, by sharing the same address, okay, you get lots more endpoints. So in practice, we have 65,000 ports available to each endpoint. So if you have your iPhone or you have your laptop, you have 65,000 processes, applications that could be running on it at any given moment in time, but you're only using one address. And addresses, for various historical reasons, are scarce. Now, you could imagine building a network where you only have very long addresses and they uniquely identify every endpoint. You could do that, but that's not what we do. It's just a historical thing. Yeah?
So say your cell phone, right?
Yeah.
You're connected to like several different several ports.
Yeah.
Now, does your address change every time you change a port?
No. So the address remains the same, and what happens is that you get different ports.
Oh, okay.
So the overall destination is determined by the composition of the addition of the concatenation of the address and the port.
Okay.
Yeah.
So if there's like billions of addresses, won't that run out?
Yeah, they have run out.
Oh yeah.
Yeah, IPv4, which is 32 bits, which is 4 billion addresses, it has run out.
Yeah.
Yeah, so I'll talk about that in just about 2 minutes from now. Yeah, but yes, absolutely, that has happened already. Okay. When it was designed, they only had 16 computers on the internet. They said, we'll never get there. This is what's called a success disaster. Okay. It's a wonderful problem to have. Okay. Yeah, may you all have success disasters. Okay. It's like saying, oh, my psychotherapy bills are so high because I'm a billionaire. That's a success disaster. Okay. Any other questions about this? Okay, so there are actually, as it happens, two ways of communicating between here and here that are in common practice. Okay, this so-called pipe. Okay, we can think of it as a virtual pipe, sort of like a pipe. Because from our perspective, we're sending a connection on this pipe. And one of them is called Tin Can Control Protocol. Oh, no, sorry. No, it's called Transmission Control Protocol. Yeah. And the other one is called UDP, User Datagram Protocol. But TCP really is a Tin Can Control Protocol. Okay? It's kind of, it says, I want to establish this connection from here to here. So the internet is kind of funny. At the bottom level, you actually have, well, it depends what bottom means, but for the purposes of today's lecture, at the bottom level, we have packets, like so datagrams. But on top of that, we overlay the abstraction of a connection. Okay, we say, yeah, it looks as if I have a connection. That's what TCP looks like. Okay, TCP says, give me a connection. What it really means is that, I have a virtual connection from here to here, and then every time I send some data on that, it goes on that same path. I don't actually own that path, but it's going to be sent on that. With UDP, what happens is you have to individually send these separate datagrams, okay? And the details of what they do and how they do it will come to in a few weeks from now. But for now, we'll just focus on TCP, okay? Because that's what almost all applications use. From the perspective of the application, if you're writing an application using TCP, all you really need to know is that you open a TCP connection from here to here, and you essentially have a virtual tin can. Okay? You can send to some destination and some data, it'll be received over here, and then they can send data to you and you'll get it. So it's a full duplex connection. Okay? Now, what does this address look like? This address is what's called an IP address. So it turns out TCP doesn't have its own addresses. It actually uses something called IP address, which stands for Internet Protocol Address. And as a recall from last time, all of you know what an IP address is, at least you've seen it. It's basically 32 bits written in the form, so A.B.C.D, where A, B, C, D are all in the range 0 to 255, right? So like 129.97.2.1 would be, for example, which actually that one is our name server. and that's a University of Waterloo address. And so those are these A.B.C.D kind of thing. Those are IP addresses. So the way you set up a TCP connection is on this interface to the internet. You send a message saying, you make a method invocation, a call, procedure call that says send to this IP address, to this port, this data, and it gets there. Okay? And the reply says, okay, send to that address and that port and that data, send that data back. And you go back and forth. Right? But we have an asymmetry in the initial part because the server is sitting there waiting for connections and the client initiates the connections. Okay? You can't have both waiting, that doesn't make any sense. And you can't have both sending because there's nobody to listen to. So some asymmetry is necessary, and that's why we have this over here. Okay. Any questions about that so far? Yeah.
So TCP is like a connection oriented?
Yes. Okay. It's connection oriented, layered on a connectionless datagram. But from our perspective, it's connection oriented. Okay. Any other? Yes.
You mentioned that it doesn't make sense to have two clients, but what if you are, for example, you're Skype calling somebody?
Yeah.
So it's like both are clients.
Correct, and that's where it gets kind of messy. So the way Skype does it, and we'll talk about that in 2 lectures from now, is actually this is sort of a hidden server. And you both connect to the server, and then the server puts those together. Yeah. Okay, so let's go to that. IP addresses we kind of have to know a little bit about IP addresses, unfortunately. One is, of course, we know that they're running out. We'll come to that later. But one thing we do need to know right away is that IP addresses fall into 2 classes, which are called private and public. Okay. Is that visible from there? I need to stand on this side? Okay. So a public IP address, by definition, is reachable from everywhere. Okay. So if you have a public IP address, no matter where you're on the internet, you should be able to reach it, unless some network is down or something like that. It's basically reachable. Okay. Now, however, there are some addresses which have been defined to be private. And by private, what they mean is that these are not reachable. Okay, these are local. These have no meaning outside of your local domain. Okay, so let's go back to our tin can and string analogy over here. Now, we have this lawyer over here. Let's say that there is some lawyer over here, okay, who has some lawyer ID 10, okay. Now, let's say the public address is L10. So L10 means, let me just be more precise over here. Let's say the IP address, I'm going to get messed up with this. So let me just keep this straightforward. I'm going to use a home network because I think it's easier this way. So let's say you have a home, and in this home, you have a desktop computer and you have a printer. It's a printer is a P, and it's a desktop computer over here. And then you have some internet connection through some ISP over here. Okay. Now, that printer is not going to be used by anybody but this desktop computer. Okay. That printer is something that the rest of the world doesn't care about, and actually probably shouldn't get access to anyway, because you don't want random people coming in and printing stuff on your printer at home, right? It's your private printer. Why would you want to give it to anybody else, right? So it makes sense for us to have these so-called private addresses just from, common sense reasons, right? So what we'd like to do is to give it some address which looks like an IP address, but we want to make sure nobody else is ever going to use it or will use it. So for these reasons, we define a certain range of IP addresses, okay, which are always going to be private. Nobody can reach them, okay? And by nobody can reach them, I mean that when a router over here, for example, this router over here gets a private address, it won't go outside. It will just keep it inside the local domain, okay? So that one's a bit complicated, but let's sit over here. There's a router over here, right? This is the router that's connecting your home to the rest of the world. If that router were to get a private address, it's going to drop it, okay? And if at that router, if somebody's trying to send a message to it from the outside trying to get in, it will drop that as well. It's guaranteed not to send those packets as a private. Now, of course, you have your local router inside here as well. And this router similarly will only we will never send a private IP address out on that link. Okay, so the private addresses are kept in their own little spaces. Okay, so that is the need for and the meaning of a private address. Private address means you own it, it's going to be here, it won't leave a very, very tightly controlled zone. The range of IP addresses for private addresses, there are two widely used ranges, and one of them is 10 dot star, which means 10 followed by anything is a private address. Okay, 10.1.2.3, 10.5, 10.37.255, whatever, 10 dot anything is private, and 192.168 dot star, which means you have something dot something else. Okay, these are private, both of these are private IP address ranges. Okay, how many are in this range? Well, we have 32 bits, and this is 8, so it's 2 to the power 24 addresses are private here, and you have 2 to the power 16 addresses are private over here. And so every home, everything that's isolated by this little router can use these addresses for whatever they want. Okay, completely unregulated, and that's your private address space. And that answers your question, right? Why are you getting these addresses? Well, these are coming here. How was it assigned to you? Okay, that's assigned using something called DHCP, Dynamic Host Configuration Protocol. We'll study that later. But for the moment, all you need to know is that these are private addresses, only reachable inside a very local, tightly controlled domain. Yeah. So I'm going to give you the high-level view of something called network address translation. And then we'll discuss the details later. So one thing that's unfortunate about networking is that there are lots of acronyms, okay? So IP, TCP, UDP, you've already seen all of those. Here's one more acronym for you, NAT. Okay, for those of you who've seen it before, NATs, this is what a network is. So how does this work, okay? So we have a home here, and it has a private network, which is, let's say, 192.168 dot something, okay? And here is the internet. And here, let's say, is google.ca, which is some public IP address. I think it's 179.97, I don't remember actually, I'll just make it up, .64.2, okay, something like that. Okay, so let's see what happens for packets that are going, for datagrams, which are also called packets, going from here to there, all right? So you have your desktop computer over here, and you have this router over here, your local connection point, right? It sends a message here saying, I want to send a packet to 179.9.164.2. How does it do that? Using this interface over here, right? Great, so this router gets it, says, oh yeah, sure, I know what that is. Gives it to this router over here, inside your ISP. Eventually it gets to this destination over here. Great. How does it come back? Well, we have a problem, because normally the way it would come back is that when you sent it over there, you would say my source address, right? My source address is whatever it is. Let's say if it's a public IP address, is I'm coming from so-and-so, and it's like a return address on your letter. You post a letter to somebody on the corner, you put my home address is this. When they reply back to you, look up the corner, oh yeah, sure, that's what it is, and they send it back to you. That makes sense. Here, if you have a private address, it's like saying the postal service will automatically drop that letter because it's a private address. That's not nice. So what we do instead is this. This router over here has one public address. Okay, it has one public address that is shared by everybody inside this space. Okay, so when this message is sent, you take this private address and you give it to this node over here. What it does is it changes the source address. Well, don't worry about what it does. It changes the source address to this public address. Okay, and keeps a little table somewhere saying, I got this message. If somebody replies to me with this mark on it, I put a special mark on it, I'm going to give it back to this guy, because there may be more than one over here. Okay? Now our problem is basically solved. So you give this address over here. This changes the source address. It goes all the way there. Google says, oh yeah, that came from this address. Sure, I'm going to send it back. Sends it back over here. This guy says, aha, that was specially marked. And what I'm going to do is I'm going to give it back to the person who sent it to me. Okay? And this is translating, changing the source address. And so we call that address translation. So it's network address translation. It's helpful for many, many reasons. Okay? One reason is that we can have this notion of private addresses, right? So we can have lots of addresses over here, but they only have one public address. So remember, these public addresses have run out, okay? So we don't care. We just need one address that's relatively easy to get, okay? So we can share all the public address with a lot of private addresses, and so that expands the total available space. So that's good. And second, this guarantees that your local network is not going to be attacked because those private addresses are not reachable. Nobody can send any data to them. It gives you this protection, which is a good idea as well. And there are some other reasons as well which are not relevant at this point. But this has become extremely common. Okay. So what does this mean in practice? It means that if I have an application running over here, a server running over here at this endpoint, for example, Skype client. Okay, I'm sitting on Skype over here, and somebody wants to call me. They don't know what address to talk to because I don't have a public. They can get here, but since I didn't initiate it, this guy doesn't know where to send it back to. Everything has got to be initiated this way, and then you can get a reply back, but you can't initiate it otherwise. So one of the biggest achievements of Skype, so to speak, was to figure out a way in which to get around this whole private address problem. When we discuss Skype, I'll talk about the solution. Okay, but that's kind of the problem that you have to face. Okay, so yeah.
So what level is that?
It's been implemented. It's
Like say residential area, for example. Like does Rogers Group are a group of apartments or houses? Do they have a private address and then there's another one?
the short answer is it can be done multiple times. Okay. You may think you have a public address over here. So typically what's going to happen is that you get an address which you think is public but may not be public. If you're Rogers, they'll give you a private address and do it yet again, okay? So it turns out that you can have 3 or 4 levels of NAT going through, one behind the other, okay? And so in practice, it gets very messy, very, very messy. Yes?
Google sends a reply, it gives your public address.
You're correct.
But that's the only piece of information it gives you.
No, there's a special mark, remember it said, and that's called the port number. It's a special mark that you put over there which says, if I get a reply from Google with my mark on it, I'm going to give it to this guy, not to that guy. Okay, that's what you need to keep track of. It's called a NAT.
If you have several machines that all have the same port number.
So you need to make sure that, no, they all have their own private IP address and different port numbers. So we use the port number to decide. Yes?
So those different layers of NATs,
yeah.
will that be like different NAT type 1, NAT type 2?
No, the NAT types have to do with the choice of port numbers, whether they're allocated sequentially or randomly and so on. So that's what the NAT types are, the different NAT. Yeah. The multi-NAT is different from that, yeah. Sure.
Is this process inclusive of the 5 nanoseconds?
Say it again?
Is this process inclusive of the 5 nanoseconds?
No, the 5 nanoseconds number is for core routers in sort of network backbones, like deep inside the internet. Here we don't need those speeds because these connection links are only about like 10 megabits per second at most, 10, maybe 100 megabits per second. 100 megabits per second means you have 100 million packets, 100 million bits per second, right? Which is, think about it, so it's 12,000, so it's 12.5 megabytes per second, right? And one packet is about, let's say, 500 bytes, roughly speaking. So it's, let's say, it's about 500,000 packets per second. Right? So in 1 second, that's 2 microseconds you need. So 2 microseconds is still a very short time, right? But it's not like nanoseconds, which is 1,000 times faster yet. So when you start talking about networking, you quickly realize that we're in a sort of different realm altogether. Microsecond, by the end of this class, to you, 1 millisecond will feel like a very, very long time. Okay, I mean like 1 millisecond, wow, that's a long time. In 1 millisecond, you can instruct a 2 gigahertz processor can do 2 million instructions in 1 millisecond, okay? That's a lot of instructions, 2 million instructions. Okay, so speed of light is just not fast enough. Okay, that's one of the other things you realize. Speed of light, I wish it were about 100 times faster. Okay, it just isn't fast enough. This is an anecdote, and really I don't have too much time, but I should tell you that they're digging a new trench from New York to London on a straight path to shave off 4 milliseconds on the link from New York to London. Because 4 milliseconds means you can do a lot more trades. 4 milliseconds is how many? 8 million instructions, right? You can do 8 million instructions. Each trade takes whatever, 100 instructions. You can do a few 100,000 trades in those 4 milliseconds. And so these hedge funds and so on are paying for this extremely expensive fiber because they can make up that money at 4 thousandths of a second. Okay. Sorry, what? It's amazing. Yeah, there's also, they're digging trenches from New York to Chicago. New trenches are being laid. Again, straight line. I think it's called straight line networks. Okay, any other questions about this so far? So what I want to summarize by saying is that IP addresses, we have public, we have private. When we have private, applications are going to be in trouble. And we'll discuss how that works for the application layer in the next, a little bit right now in the next lecture, and then we'll come back to it later on. Okay, now I'm going to move on to the applications because I think I have everything I need about pipes. And I'm going to have to, okay, so this, I went slower than I thought. So let me, I'll talk very briefly about secure shell and NFS and spend most of my time on www. So how many of you have used SSH, a secure shell protocol? So most of you have. So I'll explain to you how it works because it's really pretty straightforward. It's the simplest possible client-server protocol. So we have a client, and that's one terminal or whatever it is, and here's a server. And what SSH does is the simplest implementation. SSH basically says, I'm going to send the data that I'm sending from the client to the server is, it's a command line. I'm going to type something. Whatever I type over here is going to be sent to the server. The server simply executes it. If you use a Unix ls command for list, it lists it. Whatever is the results of the command are sent back over here. And that's basically it. It allows you to log in to a different server. Okay? That's the guts of SSH. And from the perspective of the network, that's really all it does. All it is a way to send commands over, get results back, display them, get more commands, send them over, execute them, send them back. So you can write a remote shell kind of thing in about 5 minutes time. So why is SSH such a big deal? The reason is because it is secure. Okay? And what I mean is that on the internet today, your connections are not by default secure. If you send something, it may or may not get there, and more importantly, it can be eavesdropped. Somebody who wants to can listen to whatever you're sending. Okay? Every router can just make copies of whatever you're sending. In fact, it does. Okay? Every router on the internet core has something called a compliance port, which is required by the US government, and the compliance port makes copies of every packet that's going through, and those packets are actually sent to the NSA, the National Security Agency in Arlington in Virginia, and they keep copies of every packet going through. Okay, this is a fact. Everybody knows it. This is being done today. So every packet on the internet, more or less, is being recorded. Okay, so it's eavesdropping going on a massive scale. Okay. What SSH tries to do is to prevent that by encrypting packets. So you have some kind of way of mixing up the bits. And to set it up properly, we need some keys and key infrastructure. And so how these keys work and how all that works is actually something we'll discuss when we talk about privacy and security towards the end of the course. But for now, from the networked applications perspective, the networking part is absolutely trivial. Send a message, get it back. Okay, and that's SSH for you. Okay. All right. So the same client-server protocol is used for another system called NFS, Network File System, and I'm going to introduce this just because it's kind of a cute thing that you have. Not too many people use it or know that they're using it, but it's kind of nice anyway. So what NFS does is this. On your computer, you have a local file system, right? You have you have C drive or equivalent on a Mac, you have a volume, or in Linux, you have a drive, and you have some local directories, right? What if I could do the following? I could have my directory structure over here, I have slash something, and then I have this directory, which is actually not local. It's not on my local drive at all, but it's actually on some drive somewhere else. All right? So what would happen is every time I wanted to access that directory over here, it would actually send a message saying, give me that file. It would come back to you, and it would show it to you. Okay? What you can do then is that you can kind of have this networked file system, okay, where some data is local, some data is remote. Why would this be useful? Okay? So imagine that you have your smartphone, right? And the smartphone contains some personal information, right, that you care about, and it accidentally falls from your pocket and it breaks. Okay, you just lost all your personal information. It's not very good. But you could have done this. You could have mounted a file system at, let's say, a cloud service provider like iCloud or Amazon EC2, whatever. And when you thought you were getting the file from your local phone, you were actually getting it from Amazon. Going to suspend disbelief for a moment and assume they're always connected and the capacity of the network is fast enough that you can get through. But if that is true, then when the phone falls down, you say, no big deal, just get a new phone, connect up again, you're back in business, right? So this is what's going to happen in the next 5-6 years. Okay, by 2016, I would guess that all your personal important data is going to be residing actually in some data center somewhere, okay? And what you get, what you think is local, is going to be actually using something like network file system, okay? And because it just makes a lot of sense. You don't want to lose stuff, and we know how to back up stuff when we have, when we have dedicated staff taking care of backing up and retrieving stuff, right? So what NFS does is exactly this. So the way it works, again, the details are not important, is that we have a way to access a file, which is basically says open a file, read it, and then close the file. Or open a file, write to it, and close it. Right? That's the way we work with files in the file system. In this case, what happens is that NFS allows these open and close to happen on files that happen to be remote, and the program that is actually accessing these files doesn't even know it's happening. It's kind of being done under the covers. Okay? And that's the way NFS basically works. So on the networking side, again, all that happens is that the client sends, the client says that I want to use a file system which is on some server, okay? And the server says, I accept my files to be used by some clients. And so when the request goes to the server for a particular file, the server responds with the file. You make a local copy of it. You can read it, write it, whatever. When you're done, you write it back over here, and that's it. Okay, so that's the NFS protocol. All right, so let me move on to, okay, we are kind of, okay, I'm going to now talk about probably the more important one. This is www. I'm going to start with this. www is the World Wide Web, and it's based on the protocol. Okay, let me not actually go to the protocol. I'm going to first talk about the basic idea. So here we again have a client. And the client is what's called a browser, as you know. And the browser uses a TCP connection to talk to a web server. Okay, and it's about as simple as that. The client communicates to the web server and says, give me something. I'll explain to you what that something is. And the server gives it back. So there's a request that goes in this direction, and then there's a response that goes in this direction. So this is what's called a client-server request-response kind of protocol. And it looks like NFS. In NFS, I have a request saying, give me this file. It gives you a file back. But what we've done, what distinguishes this is that there are a few things that are different about it. One of them is that what comes back is a file called an HTML file and the hypertext markup language file. So you've probably all seen that by now. And so the request is always for an HTML file, pretty much. Okay, and it comes back with the HTML file, and that HTML file inside it contains names of other servers and other HTML files. So that's what we call a hyperlink, right? So this HTML file contains to it, within it, references, which are, and these are called URLs, Uniform Resource Locators, which are of the form, and this looks like HTTP : some server / file.html. So this is typically what a HTTP request URL looks like. So the beauty of this is that when you get one file back from the web server, you kind of have a pointer to other files you can go and get from other web servers. And they in turn can point to other web servers and so on. This, looking at it, sounds pretty straightforward. But when it came out, it was kind of revolutionary because before this, the best kind of thing out there was NFS. So NFS, you get a file, but there's nothing in that file that tells you how to use it. It just says, yeah, I have a file, right? You got a file, and you read it, you write it, whatever, but there's no semantics, there's no meaning, right? With the web, suddenly what happened was I could get a file, and I get a pointer to say, here, I can go look at the other file. You get that, you get some more pointers, and suddenly everything starts making sense because you have links. And so the basic idea is really, really straightforward. And as you know, Tim Berners-Lee invented it in a research lab, in a physics research lab. He was a physicist, actually. He was an IT guy working for physicists at CERN. And it was really straightforward, okay? But the ability to get more, suddenly triggered the growth of the web, okay? All right, so let's study how this works. There are some interesting things that the web does. The first thing it does is this use of URLs, Uniform Resource Locators, which means that I can access other resources. Okay, instead of just getting a file or just in some random format, I actually have access to other resources. So that's the first thing. The second thing, it's text-based. It's all text-based. So you can actually read the messages going past back and forth, and I'll actually give it to you what it is. And then the third thing is that the protocol itself is very simple. It only has 4 commands, actually 5 commands. So let's look at a typical request. So here's a request to get a file. It looks like this. You say get, and it's actually capital GET in English. It's very straightforward. Get, and it would be like some directories, some file, .html. And you say HTTP /1.1. So this part over here, this get part, is called the method. Sorry, this is the method. And this over here is the location. And this is the version. So it's using version 1.1. There's only 2 versions, 1.0 and 1.1 as far as I know. So that's what's going on. And then after that, you have some other, you just say host, and the URL, which is what you want to actually get. And then you say user agent, and what you're coming from. So it could be like, in this case, let's say Mozilla, which would be like a Firefox, and then accept language. EN, that means give it to me in English if you have English content. Otherwise, I'll take whatever you have. So this is pretty much what's going on. So the data that's being sent from the request is just a bunch of text. Okay. So if any of you have used the telnet command, you can just do telnet for this command on your command line. Telnet, let's say uwaterloo.ca, and you can say 80. That means connect to this name, which corresponds to a particular IP address. You'll see how that happens in a minute on port 80, and you'll be connected to the Waterloo web server. And you can just type this, get/HTTP 1.1, and that's actually all you need to do, and you'll get back the Waterloo main web page, the HTML for it. Okay, so you can just read it on your screen. It's pretty easy to do. So you can see why having English text and understandable stuff is useful. So that's the other thing that these guys do over here. text-based. What does the response look like to this text over here? The response looks like this. Something like HTTP. It says HTTP /1.1 200. Okay, and then there'll be some kind of data, and then so it'll be content type. It could be, for example, text, and then the actual data follows that. So if you try doing this, you'll actually see what content you're going to get from the web server. Okay. So what if there's an image? Then you'd say get, instead of some file HTML, you say some directory / some file.jpg, JPEG. That would be an image, and it would come back with content type over here to be image. And then over here is the image encoded in some fashion. You decode it, put it in the browser, and you have image transfer. You can do it for audio, you can do it for video, and so on. And we'll talk about YouTube. I'll discuss more about those formats. Okay. What if the file is missing? Then you get this famous message. You get 404 not found. Okay, that's the file not found 404 message, and that means it's not there. Couldn't find it. Okay, so HTTP is really this pretty straightforward protocol where you go and you get this message and you return it back. I'm going to talk a moment. I guess I have just about a moment. I'm going to talk a little bit about cookies, and we'll come back to it. We'll come back to it in a minute in the next class. So let me talk about what a cookie is, because this is something that you can explore over the weekend for yourself. A cookie is a way to track people, okay? And the way it works is like this. Each client-server communication between the web server and the web client is actually what we call stateless. It should be stateless. So you send a message, you get a reply. After that, the web server pretends it doesn't know anything about you. Okay, that was the original definition. Okay, but it kind of became a problem because if you go to Amazon and you log in first, then you go back. Okay, they don't know what you did earlier. They want to track which files did you go, which places did you go visit, what all did you buy. So you want some way to track it. And so the way it's done is like this. When the response comes back, the response has part of it something called a cookie, which is just a long number, just a string or a number, okay? And what the browser does is it keeps it in a cookie file. Stores it, right? The next time it makes a request to the same destination. So next time you go to Amazon, it will send a request and it will send the old cookie back that it had. And what the web server does is it has a cookie database, which has got sort of IP address and then cookie and then the user information. What you bought, your account number, anything they want to know about you. So let's see what happens. The first time you go to Amazon.ca or Amazon.com, your request, you say, oh, there's nothing for Amazon.ca in my cookie file. I'm not going to send anything. So Amazon is going to say, okay, I found somebody who doesn't have a cookie, so I'm going to set the cookie in the response, and the browser is going to store it in the cookie file. Unless you set this tab that says don't accept cookies, right? If you don't do that, it saves locally. Next time you contact Amazon, it says, oh yeah, this person is the one on whom I set the cookie the last time around. And so it tracks you. Okay, so each time you go to Amazon, you're going to be able to be tracked by Amazon, which one could argue is a good thing because it keeps track of your purchase history and stuff like that. On the other hand, if you are nervous about somebody tracking you, you could delete the cookie file, or you could tell your browser, don't accept cookies, something like that, and then of course they will not be able to track you. Okay, so it's up to you. So one thing you might want to do over the weekend is to just look and see what cookies you have on your browser. You can actually go. Every browser allows you to look at the cookies, and you might be surprised who all is setting cookies. So in preparing for this lecture, I went and looked at my cookie file, and I had almost 700 cookies from absolutely random places. I had no idea that they had that over there. Okay, so I'd like to just announce it for the, so don't do the third question, and we'll continue with cookies and stuff on next Tuesday. Okay.